Let's add a new theorem to our stable of theorems for geometry. This is theorem 8-1, and it has to do with a situation that we can see in this diagram here. What we've got in this diagram is we've got the altitude that is drawn from the right angle in a right triangle down to the hypotenuse of that right triangle. So in this picture, we have triangle QSR, where angle Q is 90, and segment QT is coming down and is perpendicular to segment SR. In other words, this is the altitude. This is one of the altitudes of this triangle right here, the altitude that goes from the right angle down to the hypotenuse. When that happens, the two triangles that are formed, you can see here that there's clearly two new triangles formed. They are similar to the original triangle and to each other. So in other words, in this picture, when I've drawn the altitude down here, then triangle QST is similar to triangle RQT. Got to make sure I got those letters in the right order. Triangle QST is also similar to triangle RSQ, and triangle RQT is similar to triangle RSQ. Right? These two triangles are similar to each other, and they're both similar to the original big triangle. Now that means there's a lot that we can say about this picture. We can say that, of course, that means that all corresponding angles are congruent, and also that all corresponding sides are proportional. Remember, that was the definition of similar triangles. All corresponding angles are congruent, and all the corresponding sides are proportional. And it's this part right here, the second part of that definition, that's going to lead us to really the kind of meat and bones of this section and the next two corollaries that we're going to learn about. So these aren't separately, they're not technically separate theorems from theorem 8-1. They're conclusions that we can draw based on what theorem 8-1 right here tells us. So starting with corollary 1, when that altitude is drawn down to the hypotenuse of the right triangle, so same situation we were just looking at, the length of the altitude is the geometric mean between the segments that were created out of the hypotenuse. So when we drew that altitude down, we created two shorter parts of the hypotenuse, right? The hypotenuse, this segment right here, segment SR in my diagram, was divided into segment ST and segment TR. What the corollary 1 here says is that QT will be the geometric mean between those two. And we learned in a previous video what geometric mean, what that tells us. So if QT is perpendicular to SR, then I know that QT is the geometric mean. So it's going to go here and here. It's the geometric mean between, right? So we can color code this a little bit. Sometimes that's helpful. This guy right here is the geometric mean between this segment and this segment right here. So the geometric mean goes in these two spots. ST would go on the top of one of these fractions, and then TR would go in the bottom. Right? QT is the geometric mean between these two parts of the hypotenuse. Now the second corollary is something similar. When the altitude is drawn to the hypotenuse of a right triangle, each leg is going to be the geometric mean between the altitude and the segment of the hypotenuse, that is adjacent to the leg. So, to kind of try and spell out in this diagram what that means, we have angle Q that's 90, we have segment QT that's perpendicular to segment SR. That means that this leg right here is the geometric mean between, so I know that if it's the geometric mean, it's going to go here and here. Now what is it the geometric mean between? It's the geometric mean between the altitude right here, QT, so we'll put that one right there, and the segment, the portion of the hypotenuse, the segment of the hypotenuse that's adjacent to or next to that leg. So this guy right here, ST. So that's one of these proportions that I can set up. SQ is the geometric mean between QT and ST. The other one is that the other leg, QR in this case, so QR will be the geometric mean, so it can go here and here, between the altitude, which we've already colored in here, that's QT, and the other segment of the hypotenuse, the segment that's adjacent to QR, so that would be TR. So these three relationships happen anytime I draw the altitude from the right angle down to the hypotenuse in a right triangle. Now let's take a look at a couple examples to kind of work this out and see what we can do with this. Here we have that situation. I forgot to put a right angle right there. This is the segment HJ is the altitude from the right angle down to the hypotenuse in this right triangle. JR in example A, JR is equal to 16 and EJ is equal to 9. Now we have to find HJ, RE, RH, and HE. Well, one of those is really easy to do right off the bat, right? RE, that one's not going to be too bad. I know that that's going to be 25 because I can just add 9 plus 16. Well, how can I do the others? Well, okay, here's what I'm going to do. I'm going to put variables. I'm going to put X right here. Let's see, I'll use some different colors. I'm going to put X right there. I'm going to put Y right there. And I'm going to put Z right there. These are the three things that I still need to find, right? I need to find HR, RH, that's Z that I did in blue. I need to find HE, that's the Y that I did in green. And I need to find HJ, that's the altitude that I did, the X that I did in purple, that lavender color. Well, according to the two corollaries that I learned on the previous page, I know that there are three proportions that will be true in this diagram. I know that HJ will be the geometric mean, so I can put HJ, the X, here and here, between the two segments of the hypotenuse, the 9 and the 16. 9 there and 16 there. I also know that this leg, EH, will be the geometric mean between the hypotenuse, which is X, and the portion of the the altitude X, and the segment of the hypotenuse that's adjacent to my leg that I have the Y on. So that would be the EJ segment, which has a length of 9. Then I also know that the other leg of the right triangle, Z, or HR, will be the geometric mean between the altitude, which I said is an X, and this portion of the hypotenuse that's adjacent to that leg. So that's going to be a 16. So I know these three proportions will all be true about this picture. Now if I look at this, there's only one of those that I can solve right now, right? This one I can't solve because it's got X and Z in it. I can't have two variables in something I'm trying to solve. This one's got X and Y, but you can see this one only has X. So let's go ahead and solve this. Let's say that, X squared is equal to 9 times 16, which is 144. Now if X squared is 144, then X is equal to the square root of 144, which my calculator tells me is 12. So I know that my X is equal to 12. So let's go ahead and let's take off the X and let's put in a 12 right there. Well, that also means I can put a 12 in right here and right here. So I should be able to solve these now, right? 12 times 9 equals y times y, so y squared equals 12 times 9, and 12 times 9 is 108. And now y would equal the square root of 108, and 108, that is something, the square root 108, that is something that I can simplify, because, let's see here, that is going to be 36 times 3. this equals the square root of 36 times 3. So y would equal 6 square root 3, because the square root of 36 will come out as my 6, and then that 3 stays underneath the square root. So y is equal to 6 square root 3. In this last proportion, I will have z squared equal to 12 times 16, and 12 times 16 is 192. So z is the square root of 192. Let's see, what can I divide 192 by? Well, it looks to me like I can divide 192 by 64, maybe? Yeah. Z is equal to the square root of 64 times 3. 64 is a perfect square. I can divide 192 by 64. So that means that z is equal to 8 times the square root of 3, because the square root of 64 comes out as my 8, and the 3 stays underneath the square root. So there you go. In this situation, when my variables, or when my EJ was equal to 9 and my JR was equal to 16, I can find these three values plus the 25 for ER to kind of complete that picture, if you will.